Okay, this problem is an RLC circuit. We're going to drive it at 1 megahertz. So let's put our little symbol for an RMS voltage, and the RMS voltage is 30 volts. It's connected to 1/10 ohm resistor and a 70 microhenry inductor with a 4/10 of a nanofarad capacitor. And we've got a few problems. Impedance at Z. Phase angle. What's the power factor, ladies and gentlemen? Once you know the angle, you get the power factor. Basically, you take IRMS times VRMS times the power factor, gives you the power. That's because power is only dissipated in the resistor. So the cosine of the phase angle will tell you what the component of voltage times current is in the resistor. And of course, in our phasor diagram, this makes infinite sense. Here's our phasor diagram. So this is the reactance of the inductor, reactance of the capacitor. Resistance is the reactance of the resistor. The hypotenuse is the impedance. This is the phase angle. Well, you take voltage. Remember, this phasor diagram is telling you where the current is compared to voltage. So voltage times current times the cosine of the phase angle tells you the projection of the current on the in the same direction as the voltage. So, and to get the power, we just take IRMS, VRMS times cosine of the phase angle. You can use other things. For example, V squared. We know what V is. So you go V squared over Z cosine phi. You could do that, right? Is power. Okay, here's the phasor. Done. E's done. And then the resonance frequency, which is a lot of physicists like omega. So omega equals that, and it's 2 pi f equals 1 over root LC. Okay, we've got our formulas. It's plugging and chugging now. A Z equals the square root of XL minus XC. Got to square it, plus R squared. XL is 2 pi f L times the inductance. XC is reciprocal 2 pi f C. This is a plug and chug. L is 70 microfarads, so let's go to our calculator. 70 times 10 to the negative 6 microfarads times 2 times pi times 10 to the 6th. That's our frequency. Equals. So 440 ohms. And I'm going to store it because I'm going to need it in just a second. 2 pi fc. Now that's the reciprocal of the reactance of the capacitor. So 2 times pi times 1e6 times C, capacitance is 0.4 nanofarads, 0.4 exponential -9 equals, that's the reciprocal of the reactance, so there is the reactance, 398. Okay. XL minus XC. I'm going to just make it a little dividing line. I got 41.9 ohms, and here's a reason why it's a good idea to keep things in your calculator, because you have a lot more accuracy. These two, 440 and 398, were accurate to 3 sig figs, but the difference, you lose a significant figure when you took the difference, so you want to be careful about that. So let's get back to the calculator. We got to square that, plus r squared will give us z squared. Square this, plus, what's r? 0.1 ohms. And take the square root, and there's almost no loss, so z equals 41 point, what was it? 9 ohms. Okay, B. Phi equals, well, we've already got our numbers in the calculator. Arctangent of 41.9 over a tenth of an ohm. 41.9 ohms, okay. The ohms cancel out, okay, equals. So that's 41.9, there's divided by a tenth of an ohm, and we get the tangent, or we get the inverse tangent of the angle. I got 89.9 degrees. See, the power factor cosine of the phase angle equals, well, just go back to the calculator, take the cosine of this. Very, very small, 0.00238. Okay, D, power. There we go, use this formula. We already got the cosine of phi. We multiply by b squared divided by z. Times 30 x squared, that's b squared, and then divided by the impedance, which is 41.9. Equals. So the power dissipated is, power, not resistance, power, there we go, P. Power dissipated was 0.0512 watts. This is a very good network. If you could build a radio like that, you'd be in really great shape. We've already drawn the phase diagram. F, resonance frequency. F equals 1 over 2 pi, the square root of LC, equals, let's see, 70 microhenries and 4/10 of a nanofarad. $70 microhenries times 4/10 of a nanofarad equals, take the square root, multiply it by 2 pi, equals, and now I have to take a reciprocal at the very end. So I've got 951 kilohertz, 951,000 hertz. Rounding to 3 sig figs, that is. Pretty close to 1 megahertz. Okay, that's it for this problem.